Can you start recording, please? You can see my screen, full screen?
Yes, doctor.
Okay. So in this case, how would we express P of X? P of X.
Delta Dirac X.
Exactly. So it's going to be minus F delta Dirac, for example, at the position A. Now, the potential work, okay, that's W, is equal to the integral of P of X, V approximated, times dx. Okay, now let's use this function which was proposed by, I don't remember who. So that's going to be W is equal to A1, we're going to have it outside, the integral of minus F delta Dirac X minus A. Then we have the function, which is X squared, L minus X. I'm sorry, let me erase this. X there, dx. What is this result of this integration? What's the result of this integration? Anybody? Well, let me ask somebody. This is calculus 1. Mr. Vanegas, Dylan Vanegas, Dylan Vanegas, can you hear me? Dylan Vanegas? No? Dylan Vanegas, don't make me waste time, please. How do you evaluate this integration? Remember, this is integral calculus.
I know, Miss.
No, I'm not a mister, I'm a doctor. Okay? Let's see, Mr. Daniel Paredes, do you remember how to integrate this?
Good morning, doctor. Is the with the delta Dirac function is no, I can't remember. Sorry.
You can remember. Okay, please. If this is X, okay, let's suppose this is a function of X, and we have a delta Dirac here. A. Okay. You can see immediately that except A, at A, the delta Dirac value is 0. So in this place, in between here and here, which is very small, f of x could be considered as a constant, right? So we can say that this is equal to the integration from, for example, a minus to a plus. Because everything outside this range, everything is 0, because the delta function is 0, right? So we can say that this is equal to delta Dirac x minus a, and times, let's call it all of this x equal of x. So all of this is this, dx. But in this range, this function could be considered as a constant, right? Because from a minus to a plus is the length of this interval is extremely small. So we can take this x of x outside the integral at a value a. So this is equal to minus f a1 x at a multiplied by the integral from a minus to a plus delta x dx. And what is this equal to? Anybody? Miss Puerta, this is equal to what? All of these terms. To 1, yes. This is equal to 1. So the result is equal to minus f a1 x evaluated at a. So every time you multiply the delta Dirac times a function, the integral is equal to simply the function evaluated at the point where you apply the delta Dirac. There's something that you learn in calculus. Okay, so that's something that we should remember. So in this case, you can have an approximation for the work developed by this concentrated force. And yeah, we have applied the suggestion that somebody provided. So every time you have a concentrated force, it's it's very difficult to expect an exact solution, because the concentrated force gives you a spike in general. So that will give you a change in slope of the shear of the bending moment. So it's quite difficult to expect to have an adequate solution if you have a concentrated force. But still, we can apply it. We can apply it. Now, in the future, for example, when we go to finite elements, what we do is we apply something similar to Rayleigh-Ritz, but instead of applying with one single function, okay, and to approximate the whole, the solution in the whole domain, what we do is we break this approximation in small pieces. And each one of these pieces is a finite element. So it's much more efficient, right, than trying to imagine one single function for the whole domain. Okay, so that's that. But that will be in the next semester. Right now, Rayleigh-Ritz, what it does is approximates the solution using a group of functions which satisfy the geometric boundary conditions. That's what we do. Okay, that's what we do. Okay, we identify the boundary conditions, geometric boundary conditions. Think of a system that satisfy these geometric boundary conditions, include a parameter, we call it an amplitude, some other people call generalized coordinates or something like that, okay? And starting with these proposed approximations, we try to find the best what we can do. And the best what we can do is differentiate the potential energy with respect to these amplitudes, these generalized coordinates, and obtain the minimum in some way, okay? And as we have done in this example, you can think of other ways to approximate the solutions, right? And yeah, you can get different answers. And as you can get closer to the correct solution, you can get better approximations to the deflections, of course. Okay. Is there any questions about these people, about this procedure? Any questions about this procedure, people?
Yes, doctor. This method is only for lateral loads, or not?
Yeah, well, but we can use it for other loads, okay? For example, you can remember that U, right? In general, can be calculated, or can be, calculated as 1/2 sigma x squared over E dV, right? And this, for example, in the case of axial load, could be equal to P over A squared. And you can include the effect of axial loads too. Yeah. And we can go on and, for example, calculate the cases where we have torsion. We're not going to do that in this class. We're going to concentrate in bending, but you can apply it in some other ways too. Yeah. Mr. Dominguez?
Yes, doctor, thank you.
No problem. Any other question, people? Okay. The last topic of this chapter is how to calculate the critical load of a column, okay, using conservation of energy, okay? I don't know if we will have the time in the chapter on plate theory, which is next. At the end of the chapter, we could try to include a small comment on how to apply this procedure, conservation of energy, to calculate the critical stress of plates, okay? The plating on the deck, for example, are subject to compression stresses. And these compression stresses may cause buckling. So in that case, we should be always worried about designing a ship which has enough thickness so that we can, in general situation, avoid this buckling problem. Okay, so we're going to do this for the column, but eventually we could apply this procedure to the case of the plate. Okay, so we're going to do conservation of energy. Okay, conservation of energy, remember, means that the work developed by a load equals this energy, which is developed during this work, is stored inside the column. Okay, we're going to use this principle. Okay, so in general, when we study buckling, okay, maybe we should write this word, buckling. Okay, when we study buckling, okay, the reference situation, the reference case is the the simply supported column. Okay, so we have a column, constant section, simply supported on both ends, and we applied a horizontal, absolutely horizontal force. So this is the case. Now, we have to be careful, okay? Because maybe you remember from your solid mechanics class, okay, that this case can be analyzed with this equation, okay? So this is EI sub C, V comma 1, 2, 3, 4. In this case, this is a compressive force, so we have positive sign, V comma XX, and this is equal to 0. So you review this in your class notes, right? So immediately, this is an homogeneous problem. And you see that here, I have the fourth derivative. Here, I have the second derivative of V. And there are no terms which are independent of V. That's why we call it homogeneous, okay? If there were any term independent of V, we would put it on the right-hand side, but there are none, okay? What's the problem with this? The problem with this is that V equal to 0, it's a solution. So the trivial solution is possible. That's V of X identically equal to 0 is possible, right? If you take this and put it into here, the fourth derivative of v is 0. The second derivative of v is 0. So in this case, 0 plus 0 equal to 0. That's the solution. Okay, so let's write up here. That's why I left this space. Okay, so I'm going to start like this. Okay, here we have something like this, and we apply a small force. You see that this force is compressive. That's why in the equation here, we use positive sign. Okay. Now, V, remember, V is the deflection. So in this direction, I measure V. But since this is a homogeneous problem, V is identically equal to 0. So that means that the right end moves a little bit because we are applying a compressive force, but does not deflect. Okay, I don't know, where am I? This is U. So you have a column, apply force, and the end moves to the left, reducing the length of the column. But since this is a homogeneous problem, there is no deflection in the lateral direction. Now, let's increase that force. So what we do is we are going to increase this, this vector here. I'm going to add, because of this increment, this is going to move like this. But again, we have not reached what we call the critical force. So we have no deflection again. Okay, now let's suppose that we increase this force until we are just a little bit below the critical force. Okay, so we're going to be like this. And we are very close just a little bit below what we call the critical load. Now, if you remember, the critical load is the load that even though you apply a force in this direction, there is some deflection in the lateral direction. That's what we call V. Remember, V is measured in this direction, U is measured in this direction. Just a little bit below. In this situation, let's suppose that we increase this little amount that we are missing. Okay, so if you go and find an increase by a little amount, you reach peak critical. And at that time, okay, this equation has a difference, which is different than the critical. I'm sorry, the trivial solution. Okay, it's like having, more or less, it's like having something like this. So it's like having a constant which depends on P times P to the V. That's the parallelism. If we can get this constant to be equal to 0, then V, the amplitude, could be anything. More or less, that's the situation there. Okay, we apply a force, compressive force, so that this constant is 0. That means that the amplitude in this, for the lateral deflection, could be anything. That's what we are finding. Now, what happened before, we are not going to consider. What happens if we are just a little bit below and we increase by this little amount the force, and this buckles occurs, that's what we're interested in. That's the situation that we want to calculate. So in this case, okay, the force is P critical, right? So we were a little bit below, but this little amount is just neglectable. So basically we are P critical here. And because we have reached the buckling, the column does this. And once it does this force advances. And because of this advancement, okay, this displacement, this force, which is equal to P critical, develops work. So we want to calculate the work, which is developed by this force, which advances because of the buckle of this column. Now, this work will be stored inside the column once it deforms. So all this energy, okay, because this motion is stored in here. So we have conservation of energy. Any questions about the process that I have described it? Any questions about this process, people? Did you study this problem in solid mechanics? Mr. Chin, do you remember this process, this calculation? Mr. Chin?
No, doctor.
No, come on, don't tell me that. It's obligatory. You didn't? No, I don't want to.
I don't remember.
Oh, that's different. That's different. That's different. The one thing is you didn't study. The different thing is that you didn't. You don't remember. It's different than you didn't study. Let me ask somebody, Mr. Gomez. Do you remember this topic in solid mechanics?
No, doctor.
Come
No.
on. Okay, our next session, I will say a couple of more words about it. But yeah, that's it's a very important topic. Okay, now let's go on. Okay, so again, we have a column, we apply a force slowly. Since it is a homogeneous problem, no deflection takes place at all. Right? So the trivial is the solution of this problem. That means that there is no lateral deflection. Okay. If we increase, we reach a point where we are very close to the situation that I wrote here. It's like having the product of two quantities. Okay. And one of them is equal to 0. If this A, in general, this parameter, which depends on the compressive force, is equal to 0. The other, which is basically the amplitude of the deflection, could be anything. That's our interest. So we're applying a compressive force, and because of this reaches a certain value, this happens. Even though this force is horizontal completely, causes a lateral deflection. So we're interested in knowing, okay, once we reach this value, because of this buckling, okay, this end moves axially. And since it moves, this force moves axially, develops work. So we want to calculate that work. And then we're going to see what happens inside the column. So because of this bending, there's some storing of this energy inside the column. So these two terms have to be equal to each other. And from there, we're going to get the critical force. That's the procedure. Okay, so in this figure, you see that there is a critical force. We call it P critical. Okay, so that's this critical force. Okay, this critical force is equal to this force when it reaches this critical value. So this value, the critical, is the value of the compressive force, which makes this column to buckle. Okay, that's what we're interested. Now, if this happens, this end moves in the x direction, and it moves this quantity. So we want to calculate this quantity. This quantity multiplied by this is the work developed. Now, please be careful, because in the last session, we had forces, and these forces were increasing slowly until they reached the final value. That's why we needed a 1/2. Right now, we are saying that we have reached that value, P critical. And because of this buckling, this force moves. So the force is full when it moves. So the product directly of P critical times delta U, that's going to be the work that we need to calculate. Okay, so let's do it. This is something that you have in your class notes. Okay, you have this these equations. Okay, so this is something that we had from before. Okay, mz squared over 2 ei sub c. This is the strain energy. Bending moment is equal to ei second derivative squared. So one of those we cancel with this, and we have this second derivative squared, and this is the strain energy, right? So we were like this, and because of the buckling, it's a stored energy because it adopts certain curvature. Curvature equal to 0, second derivative 0. Here, the curvature is not 0. So there is some strain inside, and that integrated is that. So that energy is that one. Okay. Now that's easy. Let's go to the other term, which is the work. This moves a delta U. That's what we want to calculate. So that's interesting now. Now, originally, let's suppose that we have this little element. The length of this element is delta S from here to here. Okay, so we're like this. If you reach buckling, that means that this element rotates. And so this element is now in this deformed position. And because of this, you see that there is a difference here. This shouldn't be delta, this should be du. Let's change it. In your class notes, please correct it. This should be du. dx, ds, ds. The result of this integration is delta u. That's the parameter that we need to calculate. Okay? So what we need to calculate is dx. Okay, so we have this triangle. Now this angle is the slope. So this is dv, dx. Okay, if we multiply this angle times dx, then this distance, vertical distance, is the slope dv dx times the distance dx. So dx is equal to ds squared minus this amount here squared. So du is the difference between ds and dx. This is ds, this is dx. The difference is du, that's what we're reaching here. This thing here comes from this triangle. Okay, so this triangle, this is a hypotenusa. So this is equal to this side, which is dx squared, this vertical side, which is equal to that. So this is ds square root of dx squared plus dv dx squared so we can take dx squared outside, and that's what you see here. And what we do is we expand this using Taylor series expansion, okay? So it's like having 1 plus x. So what we do is we say this is equal to our f of x. So Taylor series expansion say that f at x plus dx is equal to f at x plus the first derivative times dx. So we take the whole variable as this derivative is squared. So this is going to be, we expand this around 0. So we say that f at 0 plus dx. So we evaluate this at 0, that's 1, plus the derivative of this is 1/2. This to the minus 1 evaluated at 1, so it's going to be the square root of 1 and times dx. Now, what we do is we say dx is approximately equal to, here I have dx. We leave it there and that's it. So this term here is going to be equal to 1 plus 1/2. Now, the dx is the function outside the equilibrium. So the function is all of this. This is the variable. This is the variable that we're considering. So that's dv dx. The whole thing is multiplied by dx. So when we subtract these terms, cancels that term. And this is what we have here. See, this is just a Taylor series expansion. Okay. After that, we just have to integrate. That's it. So delta u is the integration over the whole column from 0 to L of these little pieces, because once you have this, you rotate and the end moves a horizontal distance. So integrating these little pieces over the whole length, that's what you obtain there. So it's the slope squared divided by 2 integrated over the whole length of the column. So you multiply this by P critical, that's the axial motion. I'm sorry, that's the work developed by the external force, the critical force. Now we have both terms, U, W, we make them equal and we get the critical force. So that's what we're going to do now. So the work developed on the left so this is delta U and this is U. So this thing here we can proceed and calculate. Okay. Now the classical case, as we said before, is the simply supported column. So it's simply supported on both ends. Okay. The solution of that, you can remember from your solid mechanics class, is the sinusoidal. Okay. So in this case, specifically for this case, okay, the solution is the sinusoidal. So that's the solution. Okay, so you can see that from here to here, that's the sine. If you continue, you can complete the cycle but we are interested only until here, which is the length. So be careful here, right? Because I'm saying pi x over L. So when x increases L, this whole angle increases pi. So half cycle. That's what we have here. Half cycle from here to here when x increases L. So we can replace this in here and here. And we can obtain the critical force for this case. So what's the second derivative of v of x, Mr. Carranza? What's the second derivative?
The second derivative.
So the first derivative, it's a p over L cosine.
Sine.
And the second derivative,
A is sine square.
what?
Sine square.
No,
P over 4. Length.
please, if you cannot differentiate these, we're in trouble. Please remember it. See, maybe you were very, very light in your calculus class, but now we have to use it. Okay, so we replace first derivative in the upper, second derivative in the upper. Please, both expressions have to be squared. Both expressions have to be squared. So remember that if you have the sine square of x is equal to 1 minus cosine of 2x over 2. Cosine square of x is equal to, anybody remembers me? 1, help me, please.
Maybe plus cosine 2x.
Exactly, not maybe. Maybe plus cosine 2x over 2. Yes, so here you have the second derivative squared, okay? So you have p over L squared, but this is squared, so you have p over L to the fourth. In the denominator, you have the second derivative, the first derivative p over L squared. So you have p over L squared, so you cancel these two. So you're gonna have p over L squared in the numerator. And that's what you have here. Okay, you replace all of this. So you cancel the amplitude, you cancel here, and this is what you obtain. Okay, so there is something which we should correct. Okay, this L should be large L. Please correct in your class notes, because this is large L and this is large L. So this is a critical, the critical force of a column, a simply supported column. This is something that you deduced in your solid mechanics class. But in this case, we did not apply, we did not solve this equation. This equation is the one that you solve in solid mechanics. This equation. We have not solved that equation. We have circumvented and high conservation of energy, but obtain the same, exactly the same result. Now, in this case, the explanation why we obtain the exact result is because we are using the exact solution. It's a sinusoidal. If you review, we can do that quickly in next session. You can review, and sinusoidal is the exact solution for the buckling of the simply supported column. Okay, and if you use that exact solution, of course, you should obtain the exact value for the critical force. That's what we have obtained here. Okay. Okay, and that's it for today. Please, I'm going to post an assignment. It's going to be a short one, so you can apply something from this to solve these beam problems, and something for this column problem, but with different boundary conditions. Okay. On Thursday, we're going to say a couple of words about what's going to happen next week, because of this chaotic situation of our country, I think we need to do some adjustments in our plans. Okay. If there are no more questions, then I'll see you Thursday. People, please start right away. Today, I'm going to sit right now and post the next assignment. Please, I would like next Thursday, when I ask you about the assignment, I would like to listen that some of you have already started. There are not much of a time, okay? So we are a little bit tight. So probably we will have about 10 days to complete the assignment. So please start right away. Okay, if there are no more questions, then I'll see you Thursday. Bye-bye now.
Thank you, doctor.
You're welcome.
Thank you, doctor.
Thank you, doctor.
Doctor.